In the 20th century, global power was measured in steel, oil, and industrial output. Nations rose and fell on their ability to produce tanks, aircraft, ships, and munitions at scale. But in the 21st century, a new strategic resource has eclipsed all of them. It isn't visible from satellites. It isn't stored in vast oil reserves. It doesn't roar like a jet engine. It's silicon. Microchips, semiconductors, have become the invisible backbone of modern military superiority. From hypersonic missiles to stealth aircraft, from satellite constellations to battlefield drones, from cyber warfare units to nuclear command and control systems, every modern weapon system depends on advanced integrated circuits. The side that controls the microchip supply chain increasingly controls the battlefield. This is the story of the Silicon Siege, how microchip supply chains dictate modern global military superiority, and why the next great conflict may be fought not only with missiles and tanks, but with export controls, fabrication plants, and extreme ultraviolet lithography machines. The brain inside every weapon. To understand the stakes, you have to understand what a microchip really is. At its core, a microchip is a collection of billions of transistors etched onto a tiny slice of silicon. These transistors act as switches, enabling computation. The smaller and more densely packed they are, the more powerful and energy efficient the chip becomes. In civilian life, that translates into faster smartphones, more capable laptops, and advanced AI systems. In military terms, it translates into precision, autonomy, speed, and dominance. Modern fighter jets rely on advanced processors to fuse radar, infrared, and electronic intelligence data into a single real-time battlefield picture. Missile defense systems depend on high-speed chips to detect, track, and intercept incoming threats in fractions of a second. Drones use onboard processors to navigate autonomously, recognize targets, and coordinate with other systems. Without advanced semiconductors, these systems degrade rapidly. They become slower, less precise, more vulnerable. In other words, silicon is the brain of modern warfare, the fragile web of globalization. For decades, semiconductor manufacturing has been one of the most globalized industries on Earth. The design of advanced chips is dominated by American firms like NVIDIA, AMD, Qualcomm, and Intel. The manufacturing of the most advanced chips, however, is concentrated in a handful of facilities, most notably in Taiwan and South Korea. The most advanced fabrication plant in the world belongs to Taiwan Semiconductor Manufacturing Company, or TSMC. This single company manufactures the cutting-edge chips used in everything, from Apple devices to high-performance computing clusters and advanced defense systems. South Korea's Samsung is another key player. Meanwhile, the Netherlands produces ASML's extreme ultraviolet lithography machines, devices so complex that only one company on Earth can build them. Japan supplies critical materials and components. The United States dominates chip design software and intellectual property. This is not a supply chain. It is an ecosystem, and ecosystems can be disrupted. The COVID pandemic exposed just how fragile this network is. A surge in consumer electronics demand collided with factory shutdowns, shipping bottlenecks, and geopolitical tension. The result was a global chip shortage that halted automotive production lines and delayed everything from game consoles to industrial equipment. Now imagine that same disruption during a major geopolitical conflict. Taiwan, the Silicon Keystone. Taiwan is not just another manufacturing hub. It is the keystone of the global semiconductor arch. TSMC produces the majority of the world's most advanced chips, those at 7 nanometers, 5 nanometers, and now 3 nanometers. These nodes represent the cutting edge of miniaturization and performance. Advanced military systems increasingly rely on chips at or near these nodes for AI processing, high-speed communications, and advanced signal processing. If access to these chips were cut off, entire sectors of advanced defense technology would be affected. This is why Taiwan is so strategically significant, not just for its geography in the Western Pacific, but for its fabs. If a major conflict were to erupt over Taiwan, the consequences would ripple far beyond East Asia. Global supply chains would collapse overnight. Defense production lines in the United States, Europe, and Asia would face immediate constraints. AI development could stall. Civilian industries would suffer enormous shocks. Control over Taiwan's semiconductor infrastructure is, in many ways, control over the technological future. The United States. From dominance to vulnerability, the United States invented the semiconductor industry. Silicon Valley is named for it. American firms still lead in chip design and semiconductor research. But over the past 3 decades, much of the manufacturing moved overseas, primarily to Asia. Cost efficiencies, specialization, and global integration drove this shift. By the 2020s, the United States was producing only a small fraction of the world's most advanced chips domestically. That created a strategic vulnerability. Recognizing this, Washington launched major initiatives to rebuild domestic semiconductor manufacturing. The CHIPS and Science Act committed tens of billions of dollars to incentivize new fabrication plants in the United States. Intel began expanding domestic production. TSMC announced plans to build advanced fabs in Arizona. Samsung committed to new facilities in Texas. The goal is clear: reduce reliance on foreign manufacturing for critical technologies, especially those relevant to national security. But building a cutting-edge fab is not like building a car factory. It takes years, billions of dollars, and an incredibly specialized workforce. Even with aggressive investment, reshoring advanced semiconductor manufacturing is a long-term project. In the meantime, global supply chains remain deeply interwoven. China, racing against the clock. China understands the stakes as well as anyone. For years, Beijing has pursued technological self-sufficiency under its Made in China 2025 strategy. Semiconductors are at the heart of that ambition. China imports more semiconductors by value than oil. That dependence is seen as a critical vulnerability. The United States has responded with sweeping export controls aimed at limiting China's access to advanced chips and the tools required to manufacture them. Restrictions on high-end GPUs, chip design software, and extreme ultraviolet lithography machines have tightened. These measures are designed to slow China's development of advanced AI systems and military technologies that depend on leading-edge chips. In response, China has invested heavily in domestic semiconductor firms, pouring billions into state-backed initiatives to develop indigenous capabilities. But semiconductor manufacturing at the cutting edge is one of the most complex industrial processes ever devised. Replicating decades of accumulated expertise, supplier relationships, and technical know-how is extraordinarily difficult. The result is a technological arms race, not just in weapons, but in fabs. AI and the military-edge artificial intelligence has become central to modern military planning. Autonomous drones, predictive logistics systems, real-time intelligence analysis, cyber operations, and battlefield decision support systems all depend on high-performance computing. High-performance computing depends on advanced semiconductors. Training large AI models requires massive arrays of GPUs and specialized AI accelerators. Deploying AI at the tactical edge, inside a drone, a vehicle, or a missile, requires compact, efficient, high-performance chips. If one nation can produce or access more advanced AI chips than its rival, it gains an edge not just in commercial applications, but in defense. Export controls on advanced GPUs are not just about economic competition. They are about limiting military capability. In future conflicts, AI-enabled systems may determine how quickly targets are identified, how efficiently resources are deployed, and how effectively threats are neutralized. Silicon becomes the deciding factor in speed, and speed is often the deciding factor in war. Hypersonics, cyber, and space. Consider hypersonic weapons, missiles capable of traveling at speeds greater than Mach 5 while maneuvering unpredictably. Tracking and intercepting such systems requires ultra-fast sensors, data fusion, and advanced computational models. That means advanced chips. Consider cyber warfare. Offensive and defensive cyber operations rely on massive data processing, encryption, decryption, and network analysis. Again, chips. Consider space. Satellites for communications, reconnaissance, GPS, and missile warning all depend on radiation-hardened semiconductors. As space becomes more contested, the ability to rapidly design and produce resilient satellite systems becomes critical. Every domain of modern warfare, land, sea, air, cyber, and space, has a silicon backbone. The choke points. What makes the semiconductor ecosystem so strategically powerful are its choke points. Extreme ultraviolet lithography machines, produced only by ASML in the Netherlands, are required to manufacture the most advanced chips. These machines contain hundreds of thousands of parts and rely on supply chains spanning multiple countries. The United States controls critical semiconductor design software and intellectual property cores. Japan controls key materials and specialty chemicals. Taiwan and South Korea dominate advanced fabrication. These choke points can be weaponized through export controls and sanctions, but weaponizing them carries risks. Overuse of export restrictions can incentivize competitors to accelerate domestic alternatives. Supply chain decoupling can fragment the global market, raising costs and slowing innovation. The Silicon Siege is not just about who has the most advanced chips. It is about who controls the bottlenecks. Economic warfare as precursor to military conflict. Historically, blockades and resource embargoes have preceded major wars. Today, export controls on semiconductors function as a kind of digital blockade. Restricting access to advanced chips can cripple a nation's ability to develop next-generation weapon systems. It can slow AI research. It can limit supercomputing capacity. This form of economic warfare operates below the threshold of kinetic conflict. It is quieter, more technical, but potentially just as consequential. The line between economic policy and military strategy is blurring. The risk of over-concentration. One of the greatest risks in the current system is over-concentration. If a natural disaster, cyber attack, or military strike were to disrupt a handful of key fabs, global semiconductor output could plummet. Taiwan sits in a region prone to earthquakes and geopolitical tension. South Korea lives under the shadow of North Korean missile threats. In a worst-case scenario, semiconductor facilities could become strategic targets. The destruction of advanced fabs would not just impact one nation, it would reverberate globally. Military modernization programs could stall. AI development could freeze. Civilian industries could enter recession. The fragility of this infrastructure makes it both invaluable and vulnerable. Resilience versus efficiency. For decades, efficiency drove supply chain decisions. Companies optimized for cost, specialization, and just-in-time delivery. Now, resilience is becoming the priority. Governments are subsidizing domestic production, diversifying supply chains, and stockpiling critical components. Military planners are reassessing dependencies on foreign-made semiconductors. But resilience comes at a cost. Building redundant capacity is expensive. Maintaining stockpiles can lead to obsolescence in a rapidly evolving industry. Balancing efficiency and security is one of the defining policy challenges of our time. The next battlefield, future wars, may still be fought with ships and aircraft. But the decisive advantage may lie in the supply chains that produce the chips inside them. A nation with secure access to cutting-edge semiconductors can iterate faster, deploy smarter systems, and adapt more quickly to changing threats. A nation cut off from advanced silicon may find its weapons slower, its AI weaker, its cyber defenses more vulnerable. The silicon siege is not a metaphor. It is a strategic reality. Conclusion. Power in the palm of a hand. The most powerful weapons on Earth now depend on objects smaller than a fingernail. Microchips are the hidden infrastructure of modern military power. They enable precision, autonomy, speed, and intelligence across every domain of warfare. Control over semiconductor supply chains is becoming as strategically important as control over oil fields once was. Nations are investing billions to secure their position. Export controls and industrial policy have become tools of grand strategy. The world is entering an era where military superiority is inseparable from technological supply chain dominance. In this new age, victory may not belong to the nation with the most tanks or ships, but to the one that controls the silicon. And in the quiet hum of fabrication plants, in the glow of ultraviolet lithography machines, in the delicate layering of atomic-scale circuits, the future balance of global power is being etched, one transistor at a time.